really high resolutions. We have really interesting things to show. So.
Great, thanks. Thanks for having me. I can't tell if the microphone's okay. Oh, okay, cool. So yeah, thanks for having me out here. It's actually my first time in Toronto. I see that all the American stereotypes of Canada are true. You guys just get snow all the time, so it's good to know. Also, this is like the warmest room I've been in Canada, so thank you for that. It's really cozy in here. Okay, so yeah, today I'm going to talk about this galaxy cluster simulation that we have, RomulusC, which is one of the highest resolution simulations ever performed of a dense environment like a galaxy cluster, and sort of an overview of some of the science that we've been doing with this simulation. Yeah, and before I get started, I want to just shout out my collaborators, in particular, Angela Ricarte, who's a newly minted PhD student from Yale, now at the CFA, Urmila Chadiamuri, a Yale grad student joining with the CFA, and Anna Wright, a graduate student at Rutgers University, who, like me, is also on the job market. So be on the lookout for her name. She's really fantastic. Okay, so the Romulus simulations in general is this suite of large-scale, high-resolution cosmological simulations that I led as part of my PhD thesis. The sort of overall focus of these simulations is our, as I like to say, organic, free-range, locally grown supermassive black holes. In the simulation, we've focused a lot on implementing a novel approach to modeling supermassive black hole physics in simulations of this scale, namely how they are seeded, how they form in the simulation, how they grow, how they feed back into their environment, and how they dynamically evolve within their galaxies. And I'm not going to focus too much on the physics, but I'm happy to talk offline about it. But a couple highlights, right? Black holes are allowed to dynamically evolve naturally. Say during galaxy mergers, for example, they're not always assumed to be at the centers of galaxies. This is a whole other topic that I'm very interested in. I could give a whole other separate 50-minute talk just on dynamics of black holes and merging galaxies. And they also produce the feedback that we do combined with the resolution. We have a very simple feedback model that just injects energy nearby the black hole in an isotropic way. But because of the resolution, because of the method and how we do this, this naturally results in a predicted large-scale feedback, often these large collimated outflows that we'll see a little bit later on in the talk. So overall, this is a more predictive model for black holes. It avoids a lot of the assumptions used in typical cosmological simulations like this. Romulus comes in two flavors. We have a uniform volume, Romulus 25, which samples low-density environments, maybe galaxy groups and Milky Way mass galaxies. And then we also have the one I'll be focusing on today, RomulusC, a 10 to the 14 solar mass galaxy cluster zoom-in simulation. So zoom-in meaning that rather than have a whole volume, we're focusing solely on a single virialized halo. And it's RomulusC that I'll be focusing on, and it's special because, in particular, its resolution. So both Romulus simulations are run with 250 parsec spatial resolution and about 10 to the 5 solar mass resolution. And what that means is that in a cluster environment, we can get a lot of interesting information about the multi-phase structure of, for example, in this case, the gas, as well as the evolution of galaxies in the cluster down to lower masses than we could ever do with some of these large volume simulations with lower resolution. So just to drive home the point a little bit, it might be a bit hard to read, but compared to every other simulation that includes at least one galaxy cluster, all these big volume simulations, RomulusC has orders of magnitude better mass resolution and several times better spatial resolution. The only simulation that compares to RomulusC is TNG 50 from the illustrious collaboration. Their most recent volume has one cluster about the same mass as RomulusC at about the same resolution. So this is really state of the art in terms of what we can do with cluster environments. And I'll play the video again here. Right, these are a bunch of images made of the gas in the ICM of the cluster, I believe about redshift of 0.5 or 0.3, done by Irina Butsky. She's done some awesome work looking at the multi-phase structure of the ICM. But with a simulation like this, we can really study and understand the physics of galaxy clusters, the physics of galaxy evolution in dense environments better than ever before. So in this talk, I also have three different topics I'll be hitting on. I'll start at the center of the cluster, understanding the brightest cluster galaxy, the galaxy that's forming at the center of this massive cluster, as well as the effect of AGN feedback and the structure of the intracluster medium, particularly on these small scales. And then I'm going to zoom out and study and take a look at, in general, galaxies and supermassive black hole evolution within the cluster environment. So cluster member galaxies and their host black holes. How do they evolve? How is being in the cluster different than being in isolation? And then I'm going to focus on a particular type of cluster member galaxy that has recently been very interesting for people interested in low surface brightness observations, these ultra diffuse galaxies, very puffy, low mass galaxies, very low surface brightness galaxies that have been found to exist in cluster environments relatively recently. And I should say, if you have any questions, just let me know. I'll sort of pause between each of these steps, and we can you can get any questions out on each individual part as we go. So as I said, first I'll be focusing in the center of the cluster, and the brightest cluster galaxy, and as well AGN feedback and how this regulates star formation in clusters. Right, so in the simulation, I showed a little picture before. Here it is again. We get very powerful episodes of AGN feedback. Again, all of this is predicted. It's not put in by hand. This morphology, this large-scale effect of feedback is not put in by hand at all in the simulation. And we can begin with a simulation like Romulus, not only to study when you get this feedback, but also how it's affecting the gas within the cluster, right? Because we can actually resolve the multi-phase gas in the intracluster medium all the way down to the very central regions. Sorry?
How accurately can you predict magnetization and spin of a black hole?
We don't. That's what I mean by it's not put in. The feedback is done without making any assumptions about that. The feedback is done assuming that the only energy transfer is isotropic on 100 parsec scales. That's the only thing that's done in the simulation that's put in by hand. All of this large-scale collimation, which you'll see goes out to dozens of kiloparsecs, is a prediction of that small-scale, initially isotropic energy transfer. So we're not making any assumptions about jet physics and relativistic physics or anything like that. This is the result of small-scale energy transfer resulting in large-scale winds and outflows. Yeah, exactly. Fair enough. But we're not putting in anything by hand. This collimation is not something we've placed in by hand. Is my point. Right. So just to motivate this a bit, right? The centers of clusters are really interesting regions to study, in particular when it comes to the effect of AGN feedback. Right? We see in clusters like Perseus this really dynamically interesting effect of black hole feedback, causing sound waves, causing shocks to exist in the center of the cluster, which can presumably regulate cooling. And this is important, particularly for cool core clusters, where you have lots of low entropy, dense gas with very short cooling times, yet somehow is not producing a significant amount of stars in the central galaxy. So this is one of the main problems when it comes to AGN feedback. Are AGN actually able to regulate the cooling and control the cooling of gas in these cool core clusters? Do they result in the destruction of the cool core? Are they able to do it sort of simultaneously and coexist with this cool, strongly cooling gas in the center of these clusters? And it's interesting, more recently we're seeing this picture of these clusters that's also very interesting. You get this multi-phase gas where you have in the center all this cooling gas feeding a black hole, maybe possibly feeding star formation as well as powerful black hole feedback creating, say, X-ray bubbles and lobes within the gas. And so understanding how the complicated cooling within the center of these clusters interacts with AGN feedback is an important current question. And so with Romulus, we see that at redshift 0, the brightest cluster galaxy, it is disturbed. It's going through a bit of a merger, an interaction at redshift 0, but it's a red and dead galaxy, no longer forming any stars. And the stellar mass shown here as a function of the halo mass is okay. It's a bit large, but within a factor of 2 of what we have typically seen measured in brightest cluster galaxies at similar mass halos. And so something has regulated and shut off star formation in a way that creates a somewhat realistic brightest cluster galaxy. And we can look at this further by examining the star formation history. The specific star formation history is a function of time. In blue of the BCG in RomulusC, and we see it going through these periodic phases of growth, coincident with, in red, the black hole feedback. So the amount of energy being injected by the black hole is also going through some periodic phases at early times. In the points show some observational data points of the typical brightest cluster galaxy as a function of time. The diamonds in particular, I believe, are just for typically cool core clusters as we have in RomulusC. But we have this period of time right here where we have a bit of prolonged black hole feedback that also coincides with a significant drop and eventually quenching of star formation in the central BCG. And this is due to feedback from the black hole driving these large-scale collimated outflows out to very large radii. So there's this image again. We have outflows from the AGN going out to tens of kiloparsecs from the center, and yet coexisting with rotationally supported cooler gas in the very core of the cluster. Right? So the AGN, as you can see in this picture, is not destroying the gas around it. It's imparting the energy on larger scales. And it is regulating some cooling locally. If we look at a pressure map of the gas in the center of the cluster, you can see some weak shocks propagating outward due to this black hole feedback, and this can regulate cooling more locally. But again, it's this feedback coexists with this cooler, dense gas in the center of the cluster that's feeding the black hole, that's feeding star formation a bit. And looking in terms of density, we see these nice lobed regions out at these large radii, which again, similar to observed X-ray lobes blown by these active black holes. The outflows that we see are ubiquitous throughout the simulation. So these are a bunch of different times. You can see the outflows from the center, from the AGN, are kind of going all over the place. The direction is affected by the structure of gas at any given time around the black hole, as well as sort of this cluster weather that's going on. So for example, at this point in time, you can see that the outflows are a bit warped. This is actually because there's been a close approach of another galaxy that's created a shearing force at around 30 to 50 kiloparsecs from the center that's sort of pulling the outflows in one direction. And this is important because it means that this energy that's being distributed is being distributed all over. It's not just in one direction, and it's it's not just in a single direction like a chimney or something. But again, we see that this period of particularly strong feedback that starts around 8 billion years and goes for another 2 billion years is what's synonymous with this shutting off of star formation. Now, as this is going on, as the brightest cluster galaxy is shutting off star formation due to these powerful AGN outflows, it remains a cool core cluster. So this is the temperature and entropy profile for the cluster around this time. And typical of a cool core, we see that the entropy declines toward the center well below even 0.1 R200 of the cluster. And so this declining entropy profile is typical of cool cores, and again is what we really want to understand how the black hole is interacting with it. So the fact that the black hole feedback can be taking place and while a cool core exists is interesting. And to drive this point home a bit further, what I've shown here is the evolution of these profiles of entropy and cooling time profiles of the cluster as a function of time. So blue are low values, red are higher values of cooling time and entropy. These black lines represent the period when star formation is actively shutting off in the central BCG. And during this time, there's still cool, low entropy gas with short cooling times in the center. The evolution doesn't take some dramatic turn during this period of time. And to contrast that, we have this period here, which is during a merger that's happening in the cluster. So unfortunately, or fortunately, depending on your viewpoint, RomulusC happens to be going through an ongoing merger at redshift 0 with, it's about a 1-to-8 merger. But this merger is able to stir up the intracluster medium and destroy the cool core structure. And so you can see that happening here. You do see a dramatically different structure to the ICM caused by that, but not during this time when the galaxy is actually quenching. So you can quench star formation, you can regulate star formation with AGN feedback while coexisting with a normal cool core structure of your intracluster medium, which is an interesting thing to predict. What that's saying is that whatever is regulating this cooling is doing so in a relatively gentle way. The AGN is not destroying the gas around it or blowing it away, and it's not superheating it all to super high temperatures. So to understand a bit more about what's happening, I should say this is current work that I'm doing with graduate student Urmila Chadiamuri. We can, by looking at the multi-phase nature of the intracluster medium, we can understand this process a bit further. And so what this plot is showing, this little movie, is showing the evolution of the entropy profile, the average entropy profile in purple here, as well as in gray, the multi-phase gas. So this is just all the gas that's in the simulation at any given radius, the amount of it colored in white is more gas, black is less. And what you can see is at any given radius, we have a lot of low entropy gas, despite the average entropy being a certain value. And what this is reminiscent of is this idea of precipitation, that when you have a hot halo of gas, you sometimes get gas that is a little bit lower entropy than the surroundings. That gas will want to cool and sink toward the center until it reaches a radius where it has a similar entropy, and then it'll get buoyant and stay there. And if it's able to cool enough, it'll fall all the way toward the center before it reaches anything that has similar entropy. And so this gas that's actively cooling out of the ICM is the stuff that's providing the gas for star formation and for black hole activity in the cluster. And as the AGN acts, and here the particles that are directly heated by the AGN, you can see naturally go out to large radii. So they're not dramatically affecting their immediate surroundings. But as this gas gets thrown out in outflows, it's actually affecting the way that gas is cooling out of the ICM and these intermediate scales. And so at a few tens of kiloparsec scales, there's a lot less multi-phase gas that's falling in towards the center, and the entropy is actually becoming steeper towards the center. Both of those things mean that there's less ability for gas to cool out of the ICM, and when it does cool, it's less likely to fall all the way to the center before it finds something with similar entropy. And this is, like I said, similar to this idea of precipitation-regulated cooling in cluster environments, right? So this idea is that when you have this hot ICM, you get this cooling out of it that results in this sort of chaotic accretion onto black holes. This gas falls to the center, feeds black hole feedback. That feedback then pushes things back out and regulates this cooling process over time. And the result is you get the same structure that we see in some of these observations, where you get this filamentary, complicated structure of cooling gas in the centers of clusters. This is the result of this instability, this thermal instability that exists in cluster environments. And we see, like I said, in observations, we see this. This is work by Mark Voigt looking at the X-ray luminosity versus X-ray temperature in the centers of some cool core clusters. And Mark sees this evolution here where if you calculate what you'd expect this value to be at different ratios of the cooling time of gas to the free fall time of gas, you see that, first of all of this is, the relationship between X-ray luminosity and temperature is affected by this relationship predicted by cooling time to free fall time ratios of about 10 as the lower limit. And as you go to higher ratios, you transition from these blue dots, which represent multi-phase gas, and these red dots, which represent single-phase gas. So when you have lower ratios of cooling time to free fall time, you get a lot of gas cooling actively out of the ICM. That results in lots of H-alpha and these multi-phase structures that we're seeing in the centers of clusters. As you go to systems with higher values of cooling time to free fall time ratios, that gas goes away and they're able to cool less efficiently. Right? So zooming in about right around here, that limit, that transition happens at around 30 or so. And this makes sense. As your gas gets longer cooling times relative to the freefall time, it's less able to keep up with the cooling, and it's more likely that it's going to eventually find a place of buoyancy and not fall directly towards the center. So this is essentially regulating the amount of gas that's able to cool fully and fall towards the center of the cluster. And we see essentially the same evolution in RomulusC. If we look at the profile of cooling time to freefall time ratios at different times, when the cluster is actively star forming, when it's in the process of quenching, when it's finished quenching, and then during the merger when the cool core itself is destroyed, we see that the biggest transition, or most important transition, happens between when it's star forming, when gas is dramatically cooling out of the ICM and is really able to form a lot of stars. We're in this regime below 30, where we expect this multi-phase cooling gas to exist. And as the AGN feedback works, the cooling time sort of flattens out right around 30 or so, which is, again, this transition period where we'd expect regulated cooling out of the ICM. So this precipitation-regulated cooling seems to be at play in the multi-phase ICM of the RomulusC simulation, and this transition between star forming and quenched occurs as the AGN is able to regulate this cooling time to freefall time ratio by slightly changing the cooling time without disrupting the cool core structure. Right? And as this goes on, as you transition from a ratio about 10 to 30, you see that the amount of gas in the center of the cluster, this is within 0.1 R200, remains the same. So again, the AGN feedback is not pushing gas away. What it is doing, it's regulating the amount of gas that can cool, and so there's a drop in the amount of cold gas in the center as gas is sort of stopped from cooling and fueling star formation in the center of the cluster. And this is when the brightest cluster galaxy quenches. But there's still cooling going on, it's just regulated, and there's still AGN feedback going on. It's just in this sort of now regulated loop so that there's not runaway star formation, and the amount of cold gas is dramatically reduced. And so the important aspect here is that this large-scale feedback from black holes is critically important. It's important for regulating cooling of gas on these large scales, and it's able to do so while it coexists with the cool core structure of the ICM. AGN feedback doesn't destroy galaxies, it doesn't destroy the core of clusters, yet it's still able to regulate cooling in a way that can quench star formation. Sorry? In the cluster, that is something like a few tens of megayears, I think, at around that radius, at around 0.1 R500. Yeah. So we're still So the cooling times here are like 10 to the 8 years or so, or less still, right? Yeah. Yeah. So. Exactly. Right. The difference is this you're changing how this gas is being regulated. At first, it's able to cool rapidly, and that the black hole can't keep up with it, and it's forming stars. But eventually, the black hole catches up. The cooling time is pushed a little bit higher, and now you can get this self-regulated loop that a lot of the theorists have been seeing. Right. And that is something that people have been using to explain some of this dichotomy in observations. And yeah. All right. Any questions on the role of AGN feedback in quenching the BCG? All right. Okay, so the brightest cluster galaxy is interesting, and the fact that we resolved a multi-phase gas in the ICM has allowed us to do some interesting stuff understanding black hole feedback. But there's a lot more interesting galaxies in the cluster than just the central galaxy. BCGs are great, but if you just think about it, right, in clusters, there's a lot of galaxies. And in fact, if you add it up, a significant number of the overall galaxy population that exists is in groups and cluster environments. And so understanding galaxy evolution in such dense environments and how galaxies interact with these environments is an important aspect to galaxy evolution in general. The limitation being that typically when you have a simulation that has clusters, you're not resolving much below Milky Way mass galaxies. Right? But if we want to understand in a more general sense how galaxies evolve with something like Romulus, not only are we actually resolving this ram pressure effect that you can see having on lots of these galaxies, taking away their gas, we can understand it even down to dwarf galaxy scales and understand how these interactions change with different galaxy masses. And this is interesting, of course, right? Like I said, lots of galaxies exist in clusters, and yet they seem to have different properties in clusters, namely the most obvious one being that they're redder, less star-forming in dense cluster environments. Right? There's lots of evidence that galaxies interact strongly with the cluster gas. Direct evidence from these jellyfish galaxies, and really cool images like this by Yale graduate student William Kramer, where you have these long tails of gas that's being taken away by the galaxy going through the ICM, being affected by ram pressure. And these jellyfish galaxies down here from the GASP survey, for example, also see some interesting AGN activity, which might also be interesting to study. And so how this interaction with ram pressure is affecting galaxy evolution and the evolution of black holes is a really interesting problem. And so in RomulusC, we see, not surprisingly, a significant fraction of quenched galaxies compared to isolation. So this is the quenched fraction as a function of stellar mass. In blue are isolated galaxies that we took from that Romulus 25 uniform volume simulation. So galaxies that are not interacting with anything really in particular. The quench fraction goes from basically nothing at low masses and increases at higher stellar mass. In the cluster, at high mass, we match well to the Wetzel et al. 2012 observations. But then we see this uptick in quench fraction at low masses, where everything that's dwarf galaxies at like the 80 to 90% level is quenched in the cluster environment. They've lost all their gas. And so this is really interesting, and this means that dwarf galaxies in particular represent a very strong difference between isolated and cluster environments. And this difference in quenching exists even all the way out to redshift of 2. So again, looking at the quench fraction as a function of stellar mass for these two populations, you see at the low mass end, you still have significant quenching of these low mass galaxies, even at high redshift. And this is within 2 R200. The first one was within 1 R200. This is within 2 virial radii of the cluster. So you're having significant environmental effects from early times. And not only is star formation affected, but so is black hole activity, maybe not surprisingly. Right? Through interactions with the intracluster medium, the galaxies are losing their gas, and they are also losing their supply that would fuel any black hole activity. So here I'm showing the distribution of Eddington ratio as a function of stellar mass. You have the 25th, 50th, and 75th percentile of black hole Eddington ratios at different stellar masses. In the field, what we see is even at low mass galaxies, so I didn't mention this much at the beginning, but in Romulus, even low mass galaxies are allowed to have black holes, as we see in real life. And these low mass black holes and these low mass galaxies still grow, albeit at low rates, 10 to the -4 Eddington ratios, but still they're growing at least to some amount, while in the cluster environment, there's no black hole activity at all in galaxies of this mass, even among galaxies that have black holes. So you have significant quenching of black hole activity that gets a bit harder to see the difference of if you go to the highest mass galaxies with the highest mass black holes. They're not as different, but still you have a much larger population of almost completely dead black holes in these cluster member galaxies. And if we look at the evolution of this with redshift, what we see is at any given time, similar to star formation, you do still have this significant population of completely quiescent black holes in the cluster environment. But if you look at the solid line, the top 75th percentile, as time goes on, these brightest black holes become not so different from the field. So if you have a survey that's looking at AGN activity in different environments, if you're only sensitive to the brightest black holes, you may notice less of a difference in population, while in reality there's a significantly more just completely quiescent black holes in the cluster at low masses in particular. And of course, all of this removing of the fuel for both star formation and black hole activity is driven by the effect of ram pressure. As the galaxy moves through the cluster, the gas gets taken away by ram pressure. These two are just two examples of a dwarf galaxy. In fact, our most massive ultra-diffuse galaxy, I'll talk about in a second, and a Milky Way mass galaxy as it falls into the cluster. And this one is nice because you can kind of see this rotation continuing into the tail as it falls into the cluster environment. Right? But as the galaxy interacts, it's losing its gas. And we can quantify this by looking at the evolution of star formation rate and black hole activity in blue and green respectively as a function of time. And in yellow, we're showing the ram pressure from the ICM. So as the galaxies fall into the cluster, as they reach this first pericenter passage, they all have their gas removed, and star formation and black hole activity decrease rather rapidly over time. Now, what's interesting is this might lead to different or interesting correlations between black holes and their galaxies. If the evolution of the gas supply is different, maybe there's a difference in the way black holes relate to their galaxy properties. But in fact, in the cluster environment, we don't see this happening. So this is the black hole mass as a function of stellar mass in the simulation. On the left, we have the results from RomulusC 25. On the right, we have from RomulusC. And both simulations followed the same relationship between black hole mass and stellar mass. The difference is that these points are colored by Eddington ratio. So like I said before, in isolation, galaxies are significantly more likely to have black hole growth occurring. In fact, we have this population of very luminous black holes with actually slightly less mass given their stellar mass. That matches some observations by Amy Raines and Marta Voluntari. But in the cluster environment, we don't have many of these. The majority of black holes are completely quiescent in the cluster, but they still follow the same relationship. All right. Sorry, this is redshift 0. I'll show a plot about the relationship between star formation and black hole activity, but the gist is that we find the relationship to be constant with redshift. And that's okay.
So you say that basically one or two black holes take over the feedback role, and all the others are killed off as a precursor.
So when it comes to cluster galaxies, the main feedback is happening from the brightest cluster galaxy's black hole. When it comes to cluster member galaxies, as I'll show in a second, feedback actually is still important. But when it comes to just looking at a snapshot of the simulation, at any given time, like at redshift 0, most of the black holes are already dead. But in the past, their feedback could have been important to how that galaxy evolved.
The obvious galaxies right near the center, that, it should be, obviously this is what's happening in the simulation, but because the gas has to go further to get there than it does to fall into the others, maybe somewhat smaller black holes.
I see what you're saying. I think that the important thing to note is that in massive halos like this, galaxies are moving quite fast. And so the likelihood that they'd actually be able to sort of accrete this new gas is pretty low.
Black hole that's sitting still.
Exactly. All that gas is flowing towards the center because that's just the natural part of it to do. And the galaxy that's moving the least with respect to the center is the central galaxy that's sort of stable there. That's a good point. And again, it's not necessarily obvious, but it is what we see in the simulation, that these other black holes are simply mostly dead. Now, in Romulus, in RomulusC 25, what Angelo Ricarte has shown is that we predict a constant relationship between star formation rate and black hole growth in star-forming galaxies across cosmic time. And this rate is actually consistent with this rate shown in observations and stacking analysis by Mulaney et al. 2012. And this relationship remains nearly constant over time, all the way out to redshift of 4, where if you're forming more stars, you're also growing your black hole at at a faster rate. And the same relationship exists for cluster galaxies as well. Again, all the way out to redshift of 4. The difference, again, is that at redshift 0, you no longer have any real star-forming galaxies with growing black holes anymore. All the galaxies grew earlier on, but when they were growing, they had the same relationship with one another. Now, as I said, black hole activity does actually matter in these satellite galaxies, and it's really interesting. If we look at in more detail the evolution of the star formation and black hole growth in some of these cluster member galaxies, where as the galaxy falls into the cluster, in blue is star formation. As it feels that ram pressure in yellow, the star formation begins to increase. That's because ram pressure isn't just taking away gas from the galaxy, it's also compressing gas. And so as it's removing the supply of star formation, it's compressing the gas that is already there. And it can increase star formation momentarily as the ram pressure increases. And as it increases further, this effect becomes more apparent in the structure of the galaxy. Right? This galaxy is now very small and dense, and the star formation is getting even more intense. And now we're seeing an uptick in the black hole activity in green here. The black hole activity is now starting to see this increased density of gas in the center, such that eventually the black hole activity goes through a burst, and the star formation activity begins to fall rapidly. And this burst that's happening ends up resulting in powerful black hole feedback momentarily in this galaxy. Right? So this blowing a hole in the gas that already exists in the galaxy as it's being taken away by ram pressure results in this rapid decline in both black hole activity and star formation. The black hole sort of finishes the job for ram pressure in this galaxy. And this overall picture of feedback coexisting with ram pressure has been seen in the results from the GASP survey, focusing on these jellyfish galaxies in cluster environments. This is one example where you have a galaxy moving this way towards me in a cluster environment. You see at the front of it, this dense gas, this is showing gas density, surface density, that's star forming, right? And in the center, a cavity of star formation that's dominated by AGN emission. So you have black hole activity taking away gas from a galaxy as it's also being actively affected by ram pressure. Now in the simulation, we're lucky enough that we have a couple examples like this of similarly massed galaxies, one with a black hole and one without a black hole. And in this case, the dark blue is showing the star formation rate of the black hole galaxy, and the red is the black hole activity as it falls into the cluster. The time here is relative to pericenter passage. And the light blue is an example where you have a galaxy with no black hole. So again, as it falls into the cluster, its star formation declines. You have a little blip as it passes through the pericenter, and then a gradual decline over time as the gas is removed and the gas that's already there is sort of taken away slowly but surely. Right? The difference, of course, I think is quite striking that in the case where you have a black hole, the effect of ram pressure is exacerbated, that you lose your gas rapidly after the black hole goes through its burst. And so this can affect how galaxies actually finally do quench in the cluster environment. Whether it's gradual or whether it's a rapid quenching does depend on whether or not there's a black hole there that's able to become active as a result of ram pressure. And so yeah, just to remind you that we see this dramatic outflow effect as the black hole goes through this peak in activity.
So how would this change if we could dial the massive black hole? So how would you transition from one curve to the other?
That's a good question. So I'm not sure, because the accretion rate certainly depends on the mass of the black hole, but it also depends a lot on how much gas is around. So it might matter, the mass of the black hole might be secondary to whether or not the black hole is at the center of the galaxy and able to grow as rapidly or not. But yeah, my guess is if you did like maybe tune feedback to be less and less powerful as maybe one better way of doing it. If you make it less and less efficient, then you would get something that's more and more gradual over time. At least that would be my guess. Yeah. Now, I should say this only holds true for more massive galaxies. Low mass galaxies, they all quench very rapidly, whether or not they have a black hole or not, because their gas is very easily taken away. Okay, so right, so I talked about this high rate of quenching in the cluster environment, driven by ram pressure, as well as AGN activity that can become activated by ram pressure. Right, this is just kind of showing that it's interesting, this interaction with the cluster environment is critical to the evolution of these galaxies. And yet the relationship between the galaxies and their black holes overall remains the same regardless of environment. Does anyone have any further questions on this aspect before I get to the last part of this talk? Yeah?
Does all of this stripped gas add much to the gas that's already there and doing the strip?
Right, that's a good question. In terms of total mass, I don't think so, but in terms of the multi-phase structure of the ICM, I definitely think it does. So Irina Butsky had a paper looking at the multi-phase gas in the ICM, that there's lots of warm and cool gas at any given radius in the ICM, and that if you look at different regions using, say, quasar sightlines to look at the properties of gas, you get very different results in some cases if you look nearby a cluster galaxy and versus further away. So I think they're contributing to the structure of the ICM, because this gas, as it gets stripped away, doesn't immediately become sort of dispersed within the ICM, if that makes sense. That's something we're actively looking into as well. Okay, so for the final part of this talk, and hopefully I don't have to go too fast through it, is a specific type of galaxy in cluster environments called ultra-diffuse galaxies. These are galaxies that people have begun to detect over the last 5 years or so in large numbers. They've been detected before, but only recently in the hundreds of numbers in individual clusters by low surface brightness surveys. These are typically low mass galaxies that are very extended with very low surface brightness. And there's an important question of how did these galaxies come to be? What aspect of the cluster environment caused them to form? And because we have a simulation that can actually resolve the evolution of low mass galaxies self-consistently in a cluster environment, it gives us a unique opportunity to test whether or not we even get these galaxies. Spoiler, we do. And in particular, how these galaxies came to be, how they evolved to have the properties that they do. And the other spoiler is that this is all, once again, the result of ram pressure acting on galaxies to remove gas to quench star formation. And then, as we'll see, these low mass galaxies, after they get quenched, passively evolve and naturally become very low surface brightness galaxies that are similar to these observed ultra-diffuse galaxies that people have seen in clusters. All right, so just a little bit more background. Right, these galaxies have been detected in large numbers, specifically in group and cluster environments right now, although current work is being done to look for them in isolation in the field. They're interesting because of their low surface brightness, but so far, when it comes from the theoretical standpoint, the idea of their formation mechanism has been left only to idealized simulations or semi-analytic models, or cosmological simulations of isolated galaxies, or at best galaxies in lower mass groups at low resolution. Right? But being able to, like I said, study these galaxies in a simulation that can resolve them well within a massive environment as we've been observing them is really important and really interesting. And just to drive home the point of why we think they're so interesting to study, this is from Peter Van Dokkum's paper in 2015. You have this general population of galaxies we see with SDSS in this case. Milky Way is on here in terms of radius and central surface brightness. We have these low mass galaxies, low surface brightness galaxies that typically are smaller, that people found in Virgo, for example. And then we have these objects discovered by the Dragonfly survey, and more to come, more following this, that at a given surface brightness have larger sizes than we've seen before. Possibly because they're special, possibly because we haven't detected them before because we haven't been sensitive to them. And so the question, like I said, becomes, do these galaxies have a unique formation channel that requires a dense cluster environment? Have they had something happen to them that's very specific? And again, what is the specific role of their environment in driving their formation, driving these properties? So in Romulus, we can look at all of our galaxies, our 1,000 or so galaxies that exist and are well resolved in the cluster. We can find galaxies that fit the typical definition of an ultra-diffuse galaxy. Right? We fit a Sirsic profile to each galaxy. We find the ones that have a low central surface brightness and a large effective radius. This is just directly from the definition that Peter Van Dokkum made in his paper. It's an arbitrary definition for sure, but it gives us an idea of what could be happening. And so the question we ask is, given this population of galaxies, where did they come from and how did they form? And again, what is the role of the cluster environment in their formation? So the first thing to look at is their sizes as a function of stellar mass, so the size-mass relation for these galaxies. So in gray, I have plotted isolated dwarf galaxies from Romulus 25. In blue are non-ultra-diffuse galaxies in the cluster, and orange are ultra-diffuse galaxies in the cluster. And all populations roughly follow the size-mass relation. There's a lot of scatter at any given stellar mass, and that's essentially where we see the ultra-diffuse galaxy population happening. The blue points nicely follow along the relation, while the orange points are above it, but they're just a part of the overall scatter at any given stellar mass. Now, the deviation that we see at low masses, sort of flattening out at a radius of about 1 kiloparsec, I believe is just due to resolution limits in the simulation. Yeah, that's a limitation we unfortunately can't avoid. It's not a horrible limitation, but it's a limitation nonetheless. But overall, good fit to the size-mass relation, but at any given radius, the scatter is enough to produce large galaxies. Now, if we look at the effective radius as a function of central surface brightness of these galaxies, again, same coloring. Black is isolated galaxies from Romulus 25. Blue are non-UDGs in the cluster, and orange are UDGs. The diamonds here in this region represent the observed ultra-diffuse galaxies in the Coma cluster from Peter van Dokkum et al. And Lemia Maula's paper in 2017. And so based on our definition of ultra-diffuse galaxies, right, all of our stuff is in this corner here, but there's no real separation between this ambient population and ultra-diffuse galaxies. You can see the ultra-diffuse population is really just a continuation of this population into this region of low surface density and large sizes. It just so happens in the cluster, you're populating this region much more than in isolation. And again, we match well qualitatively to where the observed data points are as well. Maybe we have an issue that we lack these very large, very low surface brightness galaxies, but there's only a few of them. So this is very promising. The same can be said looking at effective radius as a function of G-band magnitude. Again, we see the similar relationship as the observed ultra-diffuse galaxies, and compared to the ambient population, the UDGs are really just a continuation of this population to larger sizes for a given G-band magnitude. So there doesn't seem to be any real separation of the ultra-diffuse galaxy and non-ultra-diffuse galaxy populations. The same is true if we look at galaxy colors. This is the distribution of G-I colors, and this is G-I as a function of G-band magnitude. Again, the same coloring. Both UDGs and non-UDGs are very red and quenched. There is this relationship that people see in clusters that are observed where lower G-band magnitude results in slightly bluer colors, but there's no difference as to whether or not you're a UDG or not UDG. This grayed area here represents the average colors from Peter van Dokkum's UDG population, which only goes to 10 to the minus 13 magnitudes or so. So you're only sensitive really to these galaxies in here. So we agree well with the colors of observed UDGs. So basically, what I'm saying here is that the baryonic content of ultra-diffuse galaxies and their morphology is not significantly special compared to the overall population. They're simply a part of the overall scatter of properties at any given stellar mass. But in the simulation, we can also look at dark matter. And again, we see the same thing happening. In terms of the dark matter halo mass, UDGs are not special compared to non-UDGs. Again, stellar mass halo mass relationship here. The big points are the UDGs and non-UDGs in the cluster taken at infall, so at the time where they reach their maximum halo mass before they get stripped away by the cluster environment, and they lie nicely on the stellar mass halo mass relationship. There's nothing special about UDGs. And then as all these galaxies fall into the cluster, they move to the left here because their dark matter from the outskirts gets taken away. But again, nothing particularly special about UDGs. Similar with the spin of the halos. This has been another mechanism that's been put forth that maybe halo spin, very high spin halos, are the reason why you get ultra-diffuse galaxies. But again, that's not the case here. UDGs and non-UDGs have similar spin, and they both have similar spin when compared to normal isolated galaxies in the Romulus 25 simulation. Overall, just looking at the properties of these galaxies and their dark matter halos, there's nothing special about them. And so the question remains, what about the cluster environment helps these galaxies form in such high numbers in dense environments? And so for that, we look at the evolution of these galaxies over time. First, looking at the size evolution. At high masses, both UDGs and non-UDGs evolve in size relative to the infall time in the same way. At lower masses, what you have is that UDGs tend to be bigger than non-UDGs, and they tend to have been bigger for longer. So they've been larger than the typical galaxy well before they fell into the cluster. So the cluster environment is not doing anything in particular to puff up these galaxies to become special. They've already have typically large sizes compared to the non-UDG galaxies before they fall in, billions of years before they fall in. Right? But remember, what we've already seen is that galaxies in cluster environments are quenched in high numbers. And this quenched fraction gets really high at these low masses. And if we look at the central surface brightness of these galaxies as a function of time relative to the quenching time of all these galaxies, this is when we see the main important difference. Right? Before these galaxies quench, they have surface brightnesses well above what would be considered to be special, to be considered ultra diffuse. But as they quench, the surface brightness declines dramatically as the stars passively evolve and get dimmer. Right? As all those young, bright blue stars die away, and you're left with lower surface brightness galaxies. Right? And the longer that these galaxies have become quenched, the lower the surface brightness is. And this is a relationship that we see in isolated galaxies as well. So there's this relationship between the central surface brightness and the stellar age, in this case the mass-weighted age of stars within 1 kiloparsec of the galaxy. Whether you're in isolation in black or in the cluster, you follow the same general trend, where the older you are, the dimmer you are in the center. Right? It just so happens that the cluster environment is really good compared to isolated galaxies at quenching dwarf galaxies. And so dwarf galaxies quench often, they quench early, they have more time to passively evolve, and you get this enhanced population of ultra diffuse galaxies. Right? And again, this is just a schematic of this. You can see this is as this galaxy falls into the cluster. So in blue is the surface brightness profile before it falls in. As it falls in, you get actually some enhanced star formation in the center, as we talked about before. And then eventually the galaxy quenches. And after it quenches, this passive evolution takes over. And you get a dimming at all radii. And eventually you become a very diffuse galaxy that would be considered, quote unquote, ultra diffuse. But the only thing happening here is early quenching that happens very commonly in clusters. Right, and this is something actually that there's observational evidence of as well. Roman and Trujillo in 2017 found this population of red ultra diffuse galaxies and compared them to this population of what they called blue ultra diffuse galaxies. Galaxies that were a bit bluer in color and had a bit brighter surface brightnesses than your typical ultra diffuse galaxies. And they looked at what would happen if you took these blue galaxies and you passively evolved their stellar population for 6 billion years. And lo and behold, you get surface brightness profiles very similar to your red ultra diffuse galaxies. I think there's some evidence, direct evidence from observations that this is occurring. This passive evolution is important in the formation of ultra diffuse galaxies. And so once again, it all comes down to ram pressure, removing gas from low mass galaxies at a much larger rate than you'd ever expect in isolated galaxy populations. And then the passive evolution results in a very low surface brightness galaxy. Now, I will want to point out that we are looking at ultra-diffuse galaxies more in different environments, and this is work being led by Anna Wright, who, as I mentioned before, is on the job market, and who's awesome. So she's been looking at ultra-diffuse galaxies in the Romulus 25 simulation as well. We find this nice relationship between halo mass and the number of ultra-diffuse galaxies that qualitatively matches the observed relationship. And then also looking at a population of isolated galaxies that are also UDG-like. And yet what we're seeing is that these isolated galaxies, right, they don't form due to ram pressure. And so they actually have a very unique formation channel. And they're H1 rich and they're highly star forming. And so we're trying to figure out more about where these isolated galaxies come from to make better predictions for upcoming surveys, low surface brightness surveys of isolated galaxies, which is exciting. So I'll leave up a sort of general summary slide of the 3 main topics I talked about, and I'll take any remaining questions about UDGs or whatever you want.
No significant difference in stellar mass between UDGs and brighter, bluer counterparts, or it's just entirely an aging effect?
In our simulation, it is, and I don't think there's evidence in observations that there's a significant difference in. I mean, the difference in stellar mass would just be that UDGs are more likely to be lower mass in clusters, right? And they represent a significant. I think that of the overall galaxy population, there's something of the order of 50% of all galaxies in the cluster are ultra-diffuse galaxies, right? So they're in large numbers in cluster environments, and they tend to be at low mass. That's the main thing. One important sort of observational thing that would be nice is more information of the dark matter halos. So as they are right now, there's interesting predictions regarding their globular cluster population, that they have very bright, luminous globular clusters, which is more typical of more massive galaxies. And so there's this idea that they may exist in larger halos. We don't see that in the simulation, but I think that's the next step, is to try to see if we can use the simulation to see if we can come to figure out why they might have enhanced globular cluster populations. One interesting avenue of that is just that they have very different star formation histories compared to just normal dwarfs, which I think is quite possible. And of course, in the simulation, unfortunately, even at this resolution, we're not actually resolving dark matter cores. So there's this idea that supernova feedback can flatten dark matter profiles and make the structure of these low mass galaxies different. And there's been interesting observations of dark matter deficient ultra diffuse galaxies. We can't really say much to that because we don't have the resolution to actually resolve those. So all of our dark matter profiles are the same and cuspy, but that's not a prediction. That's a numerical effect that we just simply wouldn't tell the difference if there was one. Sorry, that was a long answer to maybe more than what you asked. Any other questions?
You said that the ultra-diffuse galaxies have a history of being larger.
Yeah.
Does that also make it easier to strip gas from?
I think it does. So that's another thing that I should have put as a caveat here. So one worry, and I think it's a true worry, is that at the low masses we do see some over-quenching. It's too easy to strip away gas, in part because we don't resolve molecular gas in the simulation. And so we're forming stars and we're imparting feedback in relatively low density gas because that's all we can resolve. And that makes the gas naturally a bit more puffy and more susceptible to being to have ram pressure taken away from the galaxy. So to some extent, I think we're over eager in taking away gas from these galaxies. So that's one caveat. And so naturally, just with the feedback, that can make it happen. In the cluster environment in particular, it's interesting that the galaxies do tend to have larger sizes compared to isolated galaxies. Or I should say, there's a lack of small galaxies in the cluster compared to isolation. And it seems to be tied to gas angular momentum, not so much halo angular momentum, not halo spin, but gas spin. And so for some reason, low mass galaxies seem to be accreting higher angular momentum gas at early times, which again could also be affect ram pressure in a similar way as you're saying. Yeah.
I know that we can history on merger history for those UDG members. Are they more frequent or stronger than non-UDG?
Right. So we haven't specifically looked at merger history. Again, if a merger did something unique to UDGs and not non-UDGs, we would see some difference in evolution. But even in terms of surface brightness, which is the critical aspect, there's no difference in how they evolve over time. The only difference is how long they've been quenched. Only about 30% or less of the ultra-diffuse galaxies actually have a black hole in them. And that's just a prediction of the simulation. It has to do with how we seed them based on gas. So we predict a certain fraction of galaxies to have black holes. That there doesn't need to be any enhancement of having a black hole in the UDG, and they certainly aren't required to have a black hole. But that would be a really interesting idea. Yeah?
I'm sure long before you were born, people were talking about stripping of galaxies.
Yep.
City Vandenberg had something called the image galaxies, and there were NTL galaxies as well. So were they just the earliest glimpses of what you're describing here? Or?
I mean, I think that we've observed, RAM pressure happening all the time, and other cluster simulations certainly see RAM pressure happening as well. The main thing that we're adding to the picture is a simulation that actually tests this mechanism in low mass galaxies as well, and also actually resolves it better, right? Because if you have, the worse your resolution, the more the effect I'm talking about is important, where you have artificially puffier gas that can be more easily taken away. So yeah, I mean, there's nothing new about RAM pressure for sure, and it's nothing unique about Romulus that we get RAM pressure taking away gas. What is unique is that it's well resolved and that it's resolved down to low masses. Yeah.
Any more questions?
All right. Thank you so much.